Hey, welcome to this video. In here, I'm going to do a quick review session about SOX and Unit 1 content, everything related to AP Stats. And I know AP exam is coming soon and everyone was preparing for it really hard. So I hope this video will help you a lot review the details and the structures of each unit. So I will do those kind of videos unit per unit. Sometimes the content will be overlap or extended out a little bit, but most of them will be follow the curriculum of the AP Exam Center. So let's begin. This is our very first review session. So AP Stats, review of descriptive statistics. First of all, what are the types of data that we're examining? Well, we have quantitative data and categorical data, basically. Those are the two main categories that we're focused on. And in quantitative data, we are also have two categories, which is discrete and continuous. Discrete means whole numbers and continuous means always a value between two numbers. So for example, 2 and 3, you will have 2.1, 2.14, 2.147, or etc. So qualitative or categorical data are you grouping the data into categories. So it cannot be measured numerically. For example, you can categorize the colors of hat by red, blue, yellow, such as that things. And also we have univariate data, which just means one variable, and bivariate data are two variables. And just a quick review of SOX. So how are you going to describe a data? Every time you do that thing, you're going to mention those four things: shape, outlier, center, or spread. So SOX. And graphical displays of univariate data are those followings. First of all, we can use bar charts, which basically using for categorical data. And like categorical data is when you're graphing it using bar charts, you mainly just graph different bars, label the names of each under the x-axis, and be sure to have space between each bars, because that's a huge difference for you to separate that out from a histogram. And segmented bar charts are basically two variables. So it still looks like a bar chart, but instead of each bars only represent one category of variable, we have both x and y axes have variables. So one bar chart mainly contains two variables for each bar. And the frequency table contains frequency table, basically we have two-way tables. So it has marginal distribution and conditional distributions. And histogram, just as I said before, it looks really similar with the bar charts, but we just don't have the space between. So for example, it can go from 0 to 99 and from 100 to 199, such as that. Next, we have dot plot and stem and leaf plot and cumulative relative frequency plot and box plot. So just be sure to familiarize with the first two, dot plot and stem and leaf plot. So dot plot is just like you have a bunch of dots for each categories, and stem leaf plot is like you are drawing a tree and the center is the trunk and you have a lot of leaves and branches like extending out. And the cumulative relative frequency plot is also called the ogive curve. And how are you going to draw it? Or usually most of the cases you won't asking you to draw it, but the question will give you kind of that graph, and you should be able to identify that. So mostly they will have numbers labeled at the x-axis, and the y-axis mainly are the frequencies or the percentage. So for example, for number 2 it has 30%, and for number 3, I mean, it seems like it has 70%, and for number 4 it has 100%. So always remember, for an ogive curve, it will ultimately reach 100%. So it will not extend 100% or below 100%. It will always be 100% at the end. And for the box plot, I think we are pretty familiarized with it. It's just like remember the 5-number summary and the Q1, Q3, IQR, and minimum and maximum. Yeah. And so remember, those are all the quantitative variables, which is the main object that we are dealing with in AP Stats. So, but you also have to make sure you know what is the categorical data. And if a multiple choice question gives you how to identify categorical data versus quantitative data, you have to make sure that you can able to do that. Okay, moving on to interpreting graphical displays. So this is what I talked at the beginning of the video: center, shape, and spread. Also outliers. Sometimes you will be able to mention clusters or gaps, but mainly SOCs are the 4 components you will be mentioning when you asking to describe a data or a histogram most of the cases. So always remember to put that into context. You can't just say like generally it's how it looks like. You have to say, well, what is given to the question, how can I put my words into context? And that's really important. For numerical descriptions of univariate data, we have center, which has those 3 key terms: mean, mode, and median. So mean, basically you just use that formula n+1/2. Median, n+1/2 is for median, and that's how you find the location of median. It's not the value of that median. And for mean, you're just doing the same thing like we used to do. And most of the cases, the AP test won't ask you to interpret or find a mode of a data. So we can just eliminate that out. But you can also feel free to search it up if you are curious about it. And for spread, there are also a couple key terms: range, interquartile range, also known as IQR, the standard deviation. Remember, for population and sample, they have different variables or symbols. For a variance, it also has 2 symbols: S-squared and data squared. For 5-number summary, we have min, Q1, median, Q3, and maximum. And I believe S is for population and data is for sample. I think so, yes. And how to find an outlier, you will use the fence method, which the lower fence you will use Q1 minus 1.5 times IQR. For the upper one, you will use Q3 plus 1.5 times IQR. Okay. So moving on to how to summarizing a univariate data, location and position. Sorry, I was trying to adjust the screen right here. It was pretty tough for me to do that here. Okay. Okay, anyway, we have those several methods. Empirical rule, which is 68, 95, 99.7%. This is how it usually works on a normal curve. For quartiles and percentiles, it's also pretty useful. And we used z-scores a lot. This is a standardized scores. And the formula for z-score is x minus mu over theta. So basically, the question will give you a normal curve and the mean standard deviation for that, and it will ask you to find the like what percentage of that curve corresponding with what x value. So what you can do is you will use that x value, put that into the formula, and get the z-score. The standard normal curve is mostly you will label the mean as 0 and standard deviation as 1, but again, this is just a standard normal curve. Most of the cases, the question will give you a mean and standard deviation, or it will ask you to calculate the standard deviation, and in that case, you will just first find the mean and standard deviation and put that into your calculator. How to determining a data are normal? You can use graphing, which is histogram, on your calculator. Also use empirical rule, which is 68, 95, 99.7%. Normal probability plots are z and x. You will just label not label, but you will find the probability plot on your calculator, and you can see how it looks like. If it's straight, then it's normal. Like the more straight the curve it is, then the more normal the data are. So if it's pretty curvy, then you know that it's not normal. How to compare distributions, back-to-back stem plots or parallel box plots? Okay, so this is one type of stem plot. I know I didn't draw the graph for the stem plot in like the previous session, like not the previous part, but there are actually two types of stem plot, and this is a common one. So you can see at the center of the column, the 0, 1, 2, and you will have two different branches extending out from the center of the tree, basically the stem. So in here it means 10, 20, and 70. And here is 1, 3, and 5. So remember that you always count it from the left. Yeah, and the same for both sides. And parallel box plot, it's also you're gonna adjusting your screen on your calculator to have two box plots fit in one screen, and therefore you can compare like, well, how does the mean for each box plot related to each other, and how is the IQR or mean and max, etc. Okay, so yeah, so that's basically everything that I am going to cover in this video, and I hope it just gives you a general picture of how a Unit 1 or most of the cases like SOCS SOCS looks like. How are you gonna like be able to identify all of those key terms and the graphs, and how are you gonna describe the distribution? So yeah, I hope that helps, and thank you so much for. This is our second review session for AP Stats Final Review, and remember, for all of the knowledge point that I'm gonna talk about in this video, I have this separate single videos for each of those in my playlist, so also feel free to check them out. And this video will not be so long. The reason that I'm making those videos is just want to touch points on every details or parts of this unit, but it won't be too long, so this is not a video that I'm not going to reteach you everything again. This is just a final summary video for Unit 2 and basically regression. So let's jump right in. Graphical design of bivariate quantitative data. So we're using scatterplot a lot. So what does scatterplot contains? Well, whenever you're describing scatterplot, you will be able to use direction, form, strength, and context. Context is pretty important. You have to make sure that your paragraph actually contains the details, at the same time put them into the context of the problem. Correlation and linearity. So correlation, also known as R, measure of how linear data are. And R can be between -1 to 1, and it can be equal to -1 and 1. So remember, when R equal to 1, that means the data are completely linear, and at the same time when R is equal to -1, that means the data are completely nonlinear. So don't confuse yourself. If R equal to -1, then the data are completely like the data have no correlation. That is not the case. That just means that the correlation is not linear. LSRL, this is like the linear formula, like the linear equation that we're using since first grade, not first grade, but middle school. So y hat equal to a plus bx. So the reason I'm using y hat instead of y, meaning that we're using our predicted y values. So every examinations that we're doing right here is we are predict by using the model that we created. So we are not using actual y in here, but we're gonna use actual y when we are doing the residuals, but not here. So it contains slope, y-intercept, and predictions. So slope, it's b. And remember, this is also the formula that on your packet, but it's not a bad idea to remember it. B is equal to r times s sub y over s sub x. So most of the cases, the question will give you those three variables and asking you to find b. And what you're going to do is just use this formula. Y-intercept, also known as a. This is also the formula on your packet, but a is equal to y bar minus b x bar. And same thing, like if the question gives you all of those variables, you can able to find a by yourself by using this formula. And remember, slope and y-intercept, those are all the predicted values. So you can see that predictions occurs a lot of times. It contains interpolation and extrapolation. So basically, we can use our prediction to help us define whether this data or the curve that we created contain interpolation or extrapolation. What does extrapolation means? Well, it means predict outside range of data set. So, for example, if the question is asking you to find a data that is far out from our range, then using the formula that we created by the prediction won't be very accurate. So it will lead to some bias or deviation from the actual y. Therefore, that's how extrapolation occurs. And same thing for interpolation, but just opposite meaning. For residuals, you're going to use actual minus predicted, which is y minus y hat. Coefficient of determination, also known as r squared. This is also every time when you're calculating a standard deviation, you're gonna first find the variant, variance or variation of the. But the variance correspond with standard deviation, but the variation correspond with coefficient of determination, which is r squared. So this is percent of variance in y that is explained by this model. So remember, this is in y, not in x or anything else. And basically, we can say by using the model that we created, how much variance can be explained by this model for y. Take a look at outliers versus influential point. So also, I'm gonna adding a leverage point in here, and I put all of those in here. So take a look at here. Leverage point, it means outliers in terms of x. So here is a graph. We can see that the straight linear line that fits most of the data in here are the data that we create using LSRL. But here is a point that lies outside of the range for x. Therefore, it will be considered as a leverage point. Influential point means removing it changes LSRL and R. So, for example, if we have a data like right here, then if we add to our current data, then the whole straight line, like the whole line of best fit, will be little tilted to the upper direction. Therefore, it changes the whole graph LSRL and R, the correlation of x and y. For an outlier, this is in terms of residuals. So if you have a data that is far from the actual y values, or like the data that the best fit, the line of best fit, then it will be considered as an outlier. And you will also be able to know the residuals, residual plots. How are we going to identify if it's appropriate or not? First, we have to find if it's equal numbers, both above and below x-axis, and if it's fan shape or does it have any patterns. So if all of those requirements have been met, then we can say that our residual plot fits our data, so it's appropriate. Also, be able to read a computer printout is pretty important. I have my separate videos in my playlist. Remember, it's in Unit 2. Teach you step by step how to read a computer printout, and I also have exercise for you to try, so feel free to check that out. Moving on to transformations to achieve linearity. We have exponential regression and power regression, also quadratic regression. So remember, this is the situation that I taught right here. If our LSRL does not fit to our model, like our data, then it's a good time to switch to another model. So for example, if the residual plot does not show a random pattern or does not have equal numbers of residuals on the curve, on the graph, so which means that the LSRL does not fit our data, so we can either try exponential regression or power regression. Exponential regression is x versus log y, and this is how the formula has been written as y hat equal to a times b to the x exponent. And power regression is log x versus log y, which is y hat equal to a times x to bth power. So be sure to notice the difference between these formulas. If it's exponential, then our variable is always in the exponent. If it's a power regression, then our variable is the base value, but our b value is our exponent. And quadratic regression, we don't usually use it a lot, but it's not a bad idea to familiar with this equation, which is y hat equal to a times x squared plus bx plus c. There are other transformations based on the question given to you. Also, there's situations that we need to split our data. So for example, if some portion of our data fits a LSRL, but some portion of data does not, well, we have to use separate models for this data set in order to create a line of best fit. So actually, in this case, we are going to have more than one line of best fit. So it really depends on the question. And does the model work? I forgot this part almost. So we're going to check R-squared and residual plot to see if the model that we created fit our data or not. So R-squared, oh, sorry, I'm just trying to adjust the screen right here. So R-squared is, it usually, if it's percentage, then it's from 0 to 100. If it's a decimal, then it's from 0 to 1. So we really want our R-squared to be as large as possible. So if it's 99.9%, then we can put a check mark in here. Like, it means that the data is pretty fit to our model for R-squared. If it's pretty low, if for example like 1%, then we maybe doubt about our data, our model that we created. Also, the residual plot, just as I said about right here, you're going to check those three components. Okay, so moving on to exploring categorical data. There are two-way tables, which is like here, and conditional percentage, also Simpson's paradox. So remind you about Simpson's paradox. It's basically, if you have two groups of data, then each group has, like if you examining separately of those two, then each of them, for example, will showing a uprising, increasing data line, like the straight line. But if you put them into a whole picture, you examining them together to see if there's a pattern of those data, then you can see that they're actually a downward direction of the curve. So that tells you a pretty fun phenomenon, which about how, like, in what perspective are you examining those data will really result a different results on your conclusion. So that's how a Simpson's paradox works. And most of the cases, they won't ask you to create a Simpson's paradox by yourself. They will probably just asking you, like, give you two ways of creating a model to find the line of best fit of our data. And if they are counterintuitive or they are opposite to each other, then that's a good hint for you to think about Simpson's paradox. And talking about that, that's all for this video. And thank you so much for watching. Again, this is just a quick review of Unit 2 regression stuff. And we're basically focusing on bivariate data in this case. Remember that Unit 1, we focused on univariate data, which is only have one variable, but this case, since we introduced another variable, it comes to a lot of equations and models that we can use to find our line of best fit. In this video, we're going to mainly focus on Unit 3's content and mostly experimental design. So starting with some basic vocabulary. Population means the entire group of interest. Sample means subset of the population that we're examining. Parameter means number from the population, and those are some common symbols we're going to see: mu, p, beta, and data. So be sure to familiarize with those. Statistic means number from sample. Those are also the symbols that correlates with parameter, and you can see that they correspond to each other. Census means survey the entire population. And sampling Here are also some vocabularies. I know Unit 3 we have a lot of vocabularies to know, but just stick with me. Sample design and voluntary response and convenience sampling. So just a quick review of those two. A voluntary response is if, for example, you put a questionnaire to a group of people and not everyone will be volunteer to respond, right? Like some people respond to it and some don't. And when you're collecting data in that way, you have to really be careful because the reason that not everyone is willing to respond may affect the results of your data, right? Like, what are the reasons behind those people that are not willing to respond? For convenience sampling is, for example, I just stand at the door of the classroom before the bell ring, and I just like taking the response for the last 5 people who came in, or last 10 people, I mean. And that will also be a convenience sampling because you're only examining that small group of people in that specific time period, in that specific condition. So your data will very likely be biased. And what is sampling? What is simple random sampling, also known as SRS? This is the every sample of size n has the same chance. So remember that this is the formal definition for SRS. It's not like every people in the population has every chance to get in or caught on. It's the every sample of sample size has the same chance. So sample is a key term. Stratified sampling is subgroups that are different or include all in sample. So for example, if I want to take an examination for all of the students in my high school, I will take 50 students from freshman, sophomore, junior, and senior, like all the way up to the last grade that I'm calling, and I will take every students from, like, I randomly select students from each grade, and I will put them together to do my experiment. And that's how a stratified sampling looks like. And be careful not to confuse it with cluster sampling. Cluster sampling is randomly sample some subgroups to include. It also has it will has a multi-stage, and what differentiate that from stratified sampling is stratified sampling, every subgroup is different. We clearly know that they're different. But for cluster sampling, we are assumed that each subgroup don't have that much different to each other. So it doesn't matter like which group I'm taking on because all of them are similar to each other. So I can just take 1 or 2 groups to do the experiment for the whole population. Systematic sampling is randomly pick starting point and going every nth person. So also taking the example as like standing in the door of the classroom before the bell rings, and I will take examination for every 5th person I met walking the classroom, and that will be a systematic sampling. And what are some bias? Bias, we have response bias, non-response bias, voluntary response bias, and undercoverage bias. What is a response bias? It's experiment as influencing response. So response bias, so for example, if I threw out a question, but my phrasing of that question is pretty weird or it's lean to one response, so therefore the answer I got will definitely be biased because my phrasing of my question will impact the response that I got. Non-response bias is individual chosen but chooses not to participate. And that will be similar to the voluntary response, but remember that they're different responses, different bias. And non-response bias is also like I throw out a questionnaire to a group of people, but some people are not willing to respond, and I will be asking myself, well, what are the reasons behind those non-respond people that will be related to our conclusion. A voluntary response bias is volunteer to be part of the sample. So a good example for that is if you open any of the website trying to find the rating of one product or one, I don't know, professor or something, and you will see that sometimes the response are pretty skewed. it's not a bimodal graph if you're graphing onto a curve, and most likely it will be a bimodal graph, which it has a lot of people who are rating like 1 star for that, and a lot of people who are rating 5 star for that. We're assuming that 5 star is the maximum star. So what are the people that like just in the middle? Like you won't see a lot of that ratings in that situation, because most of the people who are willing to put their answers in is they have strong opinion of that product or person. But what are the people that are not having a strong opinion to that thing, maybe not willing to put their response onto it. So therefore, the data we collect is also not the true picture. And remember, that's involuntary response bias. And undercoverage bias is some group not selected. So basically, when we're doing our sample, some samples does not include it, but we still want to examining the whole population, but there's several samples that were not included in the population, so therefore definitely it will draw bias to our conclusion. Okay, and moving on to experiments. Experiments means impose a treatment randomly. So here are some key terms. Experiment, experimental units, that's the subject that we're examining. So for example, if I want to know how many teachers that blah blah blah, then the teacher will be my experimental unit. A treatment is randomly imposed, and control group, confounded variables, and lurking variables. So those two variables, make sure do not confuse with them. Confounded variable means caused by setup of experiment. Lurking variable is observations or pre-existing variables. So from the meaning, you will see the difference. The confounded variable is when you're doing the experimental setup, what are some, like sometimes you will not pay attention, or you will overlook some details that will maybe a factor to our conclusion. Therefore, that factor become a confounded variable. A lurking variable, on the other hand, is the pre-existing variables, which means even though you still pay attention to the little details when you're doing the experiment, you still have lurking variables exist. That factor you cannot change or manipulate, and that will be a lurking variable. Components of an experiment will be those four: randomization, replication, and control, also comparison. Randomization, just as I repeat again and again, that just means you randomly assign samples or randomly pick groups, experimental units. Replication is you do the trial more than one time. And that's pretty important because we cannot guarantee that we do it once, then like there's no lurking variables or confounded variables. And therefore, in order to reduce those, we're gonna repeat our sampling. For control group, it's not always required, but it's not a bad idea to put a control group on your experiments. A comparison, definitely you want to compare the results of the bivariate data, and that's the reason that we're doing a bivariate experiment, right? And some other things, blind versus double blind, block design means control stratified sample. You have to control some variables, and it's most likely will be a stratified sample. You run an experiment on each block. So basically we just same purpose. We want to reduce confounded variables or lurking variables or other factors may result or may impact our conclusion as much as we can. For a matched pairs design, it will be block of 2. So we either put our treatments into one subject or we put our treatments into twins. So basically we want to make sure that all of the other factors are stay the same except the variables that we're examining. The observational studies are no treatments, and we're only observing natural behavior. So no treatments and no experiment, and we're just basically observing the patterns by our eyes. and we will draw the conclusion. And remember that we can never draw a cause and effect conclusion from observational studies. How to run a simulation will be those steps. First, identify the component to be repeated. Second, explain how you will model outcome or assign digits. Third will be explain how you will simulate trial. Fourth will be state clearly what the response variable is. Fifth, run several trials. Sixth, analyze the response variable. Seventh, state your conclusion in context of the problem. So the terms that are underlined in green are the key things that you're going to pay attention to. And remember, I have the video for simulation in my unit, I believe it's 3 or 4, I think. I think this is a review, like basically for unit 3, but this simulation, sometimes the curriculum will put it in unit 3, sometimes it will go back to unit 4. So it really depends. But I have this video either in my unit 3 or unit 4 playlist. So if you want to take a deeper review on it, feel free to check that out. This is our 4th review session for AP Stats Final Review, and today we're gonna focus on probability, basically the contents of Unit 4. And whatever you're preparing for your AP exam in May or other tests or finals, I hope this video helps. So let's jump right in. Basic concepts. Outcome, sample space. What is sample space? It is set of all possible outcomes. So for example, if I flip a coin, then the only 2 outcomes I'm gonna get is tails or head. The event and complement. Complement, there are a couple ways you can represent it using symbols. So for example, A to the C on the top and A prime. Also, there's a way with A, there's a dot on top of it. But those are all mean the same thing, complement. So complement representing using formula just means if you want to get a probability of a complement, then you're going to use 1 minus the probability of non-complement. So probability of A, if we want to try to find the probability of complement of A. So they're opposites. Probability of an event, remember that will always be in between 0 and 1. It can be 0 and it can be 1. If it's in those 2 extreme cases, that means it's either gonna 100% occur or it's never gonna occur. But most of the cases, they will lie between these 2 numbers, and it can never exceed 1 or be negative. A theoretical probability is and empirical probabilities. Like theoretical probabilities, we're gonna use the formula to help find out. Empirical probability is based on observation. Law of large numbers is more is better. So just think about, like, the more you flip a coin, the more the outcomes, the percentage of getting tails and heads will become 50%, right? Because that's going to be closer to the true probability. So more is better. Random variable just means event as a number. So we're gonna numerically identify the outcomes of our event as numbers. Probability distributions, basically you're gonna list X or number of heads. We're still using the coin flip as our example. So we're gonna use 0, 1, 2, 3, 4. Actually, it's not flip coin, because flip coin you only have 2 outcomes. Okay, sorry, I can't remember what example we used right here, but just as in reference, okay? So those are the type of events that are gonna occur, or type of outcomes, and next to them we're gonna list the probability of those. So moving on to calculating probabilities. Independent events, if we are trying to find, for example, probability of A and B, then if A and B are independent to each other, which means they are not going to affect to each other, right? Their outcomes won't impact to others' outcome. Then we're simply just multiply them together. If they are dependent, then we're gonna use probability of A times probability of B given A. This straight bar right here means given. Disjoint events, also known as mutually exclusive. So what is that? It means that I remember the video that I taught in one of my playlists. I just said, like, imagine that you and another person, you hate each other, like you and that person hate each other. So which means that whenever occasions you occur, he or she will not occur, and same vice versa. So that's, I think, a little good example for how you remember the definition for disjoint events. And whenever that occurs, probability of A and B is equal to probability of A given B and probability of B given A. Those three probabilities will always be 0 because you and he or she cannot occur at the same time. Never, ever. Addition rule for disjoint events is going to be probability of A or B. Probability of A plus probability of B is going to be equal to this value. Addition rule for non-disjoint events is probability of A or B equal to probability of A minus, this should be plus, sorry. This is like a typo right here, but it should be plus. Probability of A plus probability of B minus probability of B, A and B. So that makes sense, right? Because if B and A can never occur at the same time, which means the probability of A and B will always equal to 0, then if we want to find the probability of A or B, we don't have to care about that n component because it will always be 0, so no change in the value. And remember that all of the probability adding up together will be 1, and this is the summation notation, which just means adding all of the components together. For multiplication rule, there are also two cases, independent events and dependent events. For independent events, it's the same formula that were used in the first example. Probability of A and B is equal to probability of A times B. Probability of A times probability of B. For dependent events, it's probability of A and B equal to probability of A times probability of B given A. And moving on to conditional probability. This is a huge part for Unit 4. And this is where probability of A given B is equal to probability of A and B over probability of B. So whenever the component that is it's in the back, so it's in the back of this given symbol, it's the probability that we're going to put in the denominator. So don't confuse with that. And this is also on your formula sheet or your packet when you actually enter the AP exam, so don't worry if you cannot remember it. Also, there's tree diagrams. So I have a lot of good examples that I talked over in Unit 4 playlist, so feel free to check that out. I won't go deep in this video, but you can always go deeper review for yourself. For probability distributions, mean and expected values were represented as this. E just shorthand for expected. And it's equal to the mu sub x, which just means the mean, right? And how are we going to calculate it by hand is we are going to find the summation of x times the probability of x for each values. And for standard deviation, it's known as standard deviation sub x is equal to the summation of square root of x minus the expected value quantity squared over n minus 1. And you know what? Most of the cases, AP Stats exam won't ask you to do standard deviation by hand. You will be very likely to met a problem that using this formula to calculate mean, but you will never show work for standard deviation. So nice thing about that is that you're just going to use your calculator, putting the values into L1 and L2 and get the standard deviation for this. How nice it is, right? And moving on to normal probabilities, we're going to use empirical rule or use z-table, or we're going to use normal CDF and inverse norm. And those two are the most important method that you're going to be master, because you're going to use it a lot on your calculator, and how nice it is, the calculator just gives you all of the messy values for you. Also, binomial probability and geometrical probability are another big concept. There are a lot of big concepts in Unit 4. I know it's a big unit. It also plays a huge chunk of questions on your exam, so just make sure you review that very hard. And what are some like prerequisite for binomial probabilities? Well, first of all, it's either going to be success or failure. There's not a third option for you. And it's same thing for geometric probabilities. For the second rule, it's probability of success is same in each trial. So same thing applies for geometric. Trials are independent. Same thing for geometric. And the fourth condition, it's different. For binomial is the fixed number of trials, or how many successes. So basically that you're going to have a fixed number of trials for how many successes you will get. While on the other hand, for geometric, you will go until first success. So see the difference between these two. Geometric is like you go all the way till you hit the first success. Well, when is the first success? We don't know. Or sometimes the question will asking you, well, what is the probability of getting the fifth trial as my first success? You're gonna go into your calculator and do all of that stuff. But for binomial, you will never encounter that type of question. And that's also a hint. If the question gives you until what like first success or not, then you're gonna use geometric. Otherwise, it's binomial. And for mean and standard deviation for these two, for binomial, the mean you're gonna use n times p. For standard deviation is square root of npq. Q is 1 minus p. Mean for geometric is 1 over p. Standard deviation is square root of q, or 1 minus p over p squared. And PDF and CDF. So PDF is probability of x equal to an exact number, while CDF is probability of x less than or equal to that number. So imagine CDF as a like some bound that you can never go exceed that. So that's the maximum value that you will get. Therefore, all of your other values is going to be less than or equal to that. Well, for PDF, it's just what is the probability of getting that exact value. So notice the difference. And simulations, we already touched that on last video, which is in Unit 3 review session. Feel free to check that out. And I also include this simulation in, I believe it's in Unit 4 playlist. So sorry about that, like AP Stats, they manipulate the simulation quite often in every year. Sometimes they put it into Unit 3, sometimes they put it into Unit 4. It really depends on what year you're testing. But the concept or knowledge are all the same, so feel free to check that out. And basically simulating probabilities and wait time simulation, yeah, just go into my playlist. This is our 5th review session for AP Stats Final Review, and today we're going to focus on random variables, basically Unit 5 stuff. So first, discrete variables. Discrete just means whole numbers. The mean or expected value for discrete variables is summation of x times probability of x. For standard deviation, we're going to use the variance first, and then we're going to square root it to find the standard deviation. So how to find a variance is summation of x minus expected value, quantity squared times the probability of each x values. And we're going to use calculator most of cases to find variance, help us to find variance and standard deviations. And I think for calculator, you will get directly for standard deviation. So you don't have to even square root the whole thing to help you find standard deviation. You're just going to put the values into L1 and L2. L1 will be your original values, and L2 will be the frequency of those values. Okay, so here is a quick example of those like different probabilities. So for example, x in this case is going to be in 5, or how many red. Yeah, I can't really remember like what example that we are actually doing in class, but this is how you're actually going to use the formula that we introduced last video. Related binomial and geometric to help you find the probabilities. So this is because each value has 1/2 of probability of success. So because we want to find 5 times that is red, or 5 of the sample spaces, like 5 values in our sample spaces that are red, we're gonna raise the quantity to 5th power. And if we only want to find one of them are red, we're gonna use 5 times 1/2 raised to the 5th power, or we're going to simply use binomial PDF in our calculator to enter all of those values in, and we will get the probability of getting one value as red. And just as those. So remember, all of those values we're going to finally adding up to 1. So, okay, so I think 5 is our sample space in this case. Yeah. Sorry, I can't really remember like what we're doing in the class for this example, but anyway, like just showing you the idea for it. I have more videos of teaching you how to find binomial and geometric PDF and CDF in Unit 4 playlist, so feel free to check that out. Okay, so moving back to Unit 5 stuff, that's just a little recap on Unit 4 binomial and geometric. And after talking about discrete variables, moving on to continuous variables, which are the variables that we're dealing with a lot. This represent all possible values, and if it's normal, then it's very good. It's good to us because we can use a lot of functions on our calculator to find different probabilities. So basically, we're just gonna enter mean and standard deviation, and if we want to find the probability percentage, we're gonna use normal normal PDF or normal CDF. If we want to find a specific X value for cutoff of a specific percentage probability that given to us, we're going to use inverse norm. And transformations, that mostly are mean and standard deviation. If we're adding two stuff for means, for example, if we're adding a specific value for our mu sub x, then what we're gonna do is actually adding that value into our mean. So simple as it is. But adding or subtracting does not impact standard deviation. Keep that in your mind. So if we are adding a value to a standard deviation, remember that the standard deviation does not change. Because think about that, we're actually just shifting our whole data to the left or to the right specific value. So the range between each data, or the data, how much distance for each data, each value in our x-axis to the origin does not change, or to the mean value. Sorry, that was kind of messy, but I hope you get my idea. For multiplying, if we are multiplying to the mean, then we're actually going to multiply that value to our mean. But remember, multiply, it also impacts standard deviation. So if we're multiplying, for example, 4 to our original standard deviation, then actually the transformation will be 4 times our original standard deviation value. And combining, also very important. This is the example that I used in my previous playlist when I'm talking about this concept, like Jim and Linda. If you want to combine two means for two group of data, then you're going to simply just adding the means together or subtracting. And for standard deviation, either you're adding or subtracting. When you're calculating the new standard deviation, you're always going to add them together. And what you're going to do is you're going to find the variance by squaring the standard deviation for each first, and then add them together, and then square root them, because what you get under the square root is the combining variance, but we want the combining standard deviation, so you have to take the square root at the end. And this is how you do a mean when you adding the two means together. Like, we are assuming that these two means are exact values, so what you're gonna do is just times 2, because adding 2 just means times 2, right? I mean, not adding 2, but adding 2 exact same mean just means times the original mean by 2 times. But when it comes to adding the exact standard deviation twice, you have to basically adding the variance together and then square root of it. So you can also write it as 2 times square root of x to the second power. So also can shorthand as square root of 2 times the standard deviation of x. So just remember that when you're times 2 of the standard deviation, you're not directly times 2 for your standard deviation. You have to find the variance first. For the variance, you times 2 and then take the square root, so it becomes square root of 2 times the original standard deviation. Okay, and that's all for this unit. And here we're gonna do inference review. This is our 6th review session for AP Stats final review. First, take a look at this diagram. We have population parameter, which separate out to 2 branches, mean mu and proportion p. For the mean, we have these 3 types of test. 1 sample, matched pairs, and 2 samples. For 1 sample, it will be 1 sample t or z-test. Remember, if the question gives you a data, most likely it will be a z-test. Matched pairs will have 1 sample t-test for difference. That's the only case for matched pairs t-test. For 2 samples, it will be 2 sample t or z-test. For proportion p, it has 2 branches, 1 sample and 2 sample. For 1 sample, we have 1 sample z-test. For 2 samples, we have 2 sample z-test. So remember, when dealing with proportions, we only have z-test to choose. While for mean, it can be either t-test or z-test. Okay. So testing the relationship between 2 categorical variables, we're going to use Kai's test of independence. While testing the relationship between 2 quantitative variables, we're using t-test for the slope of the regression line. So notice the difference here. The biggest difference is categorical versus quantitative. Chi test is always with categorical, while the test for slope, t-test for slope, will always be quantitative. And here is a chart that kind of summarizes everything again and some additional requirements. For the means, we have those amount of situations. 1 sample z, we have to check those conditions. First, data is known, population is normal, or n is greater than 30, SRS. For 2 sample z, both data are known. Both populations are normal, or both n's greater than 30. Both are SRS. 1 sample t, data is not known, SRS. Population is normal, or n is greater than 40, or n is between 15 and 40, and little skewness and no outliers, or n is less than 15 and no skewness and no outliers. So basically, the more sample size, the larger sample size you have, the more tolerance you can have on your graph. For matched pair t, we have to be sure that this is matched data. The list of differences has n greater than 40, or n between 15 and 40, and little skewness and no outliers, or n is less than 15 and no skewness and no outliers. Notice degrees of freedom is number of differences minus 1. 2 sample t, we have to check, is this independent SRS? Data are not known. Both populations are normal, or both n greater than 40, or n between 15 and 40 and little skewness and no outliers, or n less than 15, no skewness and no outliers. Degrees of freedom from calculator. For proportions, we have 2 situations, 1 sample z and 2 sample z. For 1 sample z, checking condition for SRS, NP greater than 10 and NQ greater than 10. Population at least 10 times n, or in other words, the sample that we're taking has to be less than 10% of the total population. For 2 sample z, make sure independent SRS, confidence interval, both N1P1 greater than or equal to 10, N1Q1 greater than or equal to 10, and same thing for second sample. When dealing with test, however, both N1P hat should be greater than or equal to 10, and N1Q hat should be greater than or equal to 10. Same thing for second sample, where P hat is the pooled proportion. And this is the only situation that we're going to use pooled proportion. Anywhere else, we don't use it. Both populations are 10x. Categorical variables, we only have chi-square. So chi-square goodness of fit and chi-square test of independence or homogeneity. For goodness of fit, one variable, working with counts, all expected value should be greater than 5, or all expected value greater than 1, and 80% of E is greater than 5. Degrees of freedom equal to numbers of categories minus 1. For test of independence or homogeneity, we have two categorical variables. We're working with counts. All E should be greater than 5, or all E greater than 1, and 80% of E greater than 5. Degrees of freedom is row minus 1 times column minus 1. For the slope, we have t-test for the slope of the regression line, the only test that we have for slope. Checking for residual plot shows no pattern, curved, or fan with equal number of points above and below the x-axis. We want completely randomness for residual plot. Also, residual box plot shows little skewness and no outliers. We are tolerant for little skewness. Degrees of freedom is n-2, so notice the difference here. And here is another table, not showing like the whole picture right here. But basically, like, this is another hypothesis test review, showing you different conditions, like what formulas you should use. And I will see if I can post another PDF sometime in comments, but this is basically everything you need to know. Feel free to ask me if you really want a PDF version of this. Confidence interval review. Steps for performing any confidence interval. We're gonna first name of confidence interval, second state assumptions or conditions, third give confidence interval, and fourth conclusion in context. These are the 4 main steps we've been doing over and over again in this unit, right? Inference. Not this unit, but just every chapter related to it. So confidence interval for one proportion, the assumptions are SRS, 10% rule, NP greater than 10, NQ greater than 10. Formula we're using is right here, p hat plus or minus z star times square root of pq over n. One mean, or z, is SRS, 10% condition, data is known, normal population, or n is greater than 30. We're going to use x bar plus or minus z star times standard deviation over square root of n. For one mean, or t, we're going to check SRS, 10% condition, standard deviation is not known. That's the reason that we're using t instead of z. Normal population or conditions for small, medium, and large samples are met. Therefore, we can use x bar plus or minus t star times s standard deviation for x over square root of n. For matched pair differences in population means, checking samples are matched, the list of differences is normal, or conditions for small, medium, and large samples are met. And we're going to use this formula, x bar sub d plus or minus t star times standard deviation of x d over square root of n. Differences in two population proportions, checking independent samples, both SRS, checking NP, NQ for both samples greater than 10, 10% condition for both. We're using p hat 1 minus p hat 2 plus or minus z star times square root of this whole bunch of things. Differences in two population means, or t, independent samples, both SRS, both standard deviations are not known, both populations are normal, or both satisfy conditions for small, medium, and large samples. We're going to use this equation. So notice it's pretty similar with the formula above, except we switch from z to t. Degrees of freedom should use the calculator to figure that out. For t interval, the slope of a regression line, residual plot does not show any pattern or fanning. Residual histogram or box plot shows little skewness and no outliers. Therefore, we are allowed to use t equal to b minus, this should be the null hypothesis, but most of the cases it will be 0, so it doesn't really matter. Over standard error of b, notice have to write degrees of freedom equal to n-2. And talking about that, let me see. I know this is gonna be pretty useful if I just kind of go over them pretty quick. Sorry for kind of missing the first 2 rows, but I would just say it aloud to you guys. For one sample z-test for means, we're gonna check assumptions for SRS, 10% condition, standard deviation is known, normal population, or n greater than 30. null hypothesis will be mu equal to mu 0. Test statistic will be z equal to x bar minus mu sub 0 over standard deviation over square root of n. And for 2 sample z test for means is independent samples, both SRS, 10% condition for both standard deviations are known, both populations are normal, or both n's greater than 30. Null hypothesis will be mu1 minus mu2 equal to 0, and test statistic will be z equal to x bar 1 minus x bar 2, quantity minus mu1 minus mu2 over square root of standard deviation of sample 1 squared over n1 plus standard deviation for 2 squared over n2. Okay, so that's the missing 2 rows. Yeah, and all of those stuff, you can feel free to like take a screenshot or copy them down. I won't read all of those since I think like a lot of them share similarities, but a lot of them do have little nuances have to pay attention. But it really depends on the questions. So yeah, that's all for hypothesis test. And just reinforce the 4 steps in any test. First, parameter, hypothesis or name. Second, assumptions or conditions. Third, picture, test statistic, p-value or degrees of freedom. Fourth, conclusion, have to be in context. That's why I bolded and capitalized it. Okay. And here is just a little review for when to like type 1 and type 2 error, and when to reject or when to accept. So when null hypothesis is true, but we reject null hypothesis, we have type 1 error, which is alpha. When we fail to reject null hypothesis, but in reality that null hypothesis is true, then we're fine, we're making a good decision. If we reject null hypothesis, in reality null hypothesis is false, then it's also a good decision. In reality, that's a power. Power just means we successfully reject the wrong null hypothesis. But if we fail to reject null hypothesis, knowing null hypothesis is false, then we made a type 2 error, which is beta. So yeah. Yeah. And it's really hard to say like which one is more meaningful or which one is more which one is more harmful or something. Like it really depends on your question. So if your question is like anyway, like if your question says like a guilty man, will he be sent to the jail or will he let it go to the world? It would definitely be harder. It would definitely actually be more harmful for let him to go to normal life, right? So that's the situation when you fail to reject the null hypothesis, but null hypothesis is false. So our null hypothesis in that case will be assuming that he is innocent, which in reality he is not. But we still fail to reject null hypothesis, so we let him go. So maybe he will do something even harsher than what he already did. So it really depends on the question, right? So I can't really give you a exact conclusion for alpha or beta, which one is more powerful. Yeah, just pay close attention to the questions. And talking about that, that's all for this video, and this is our sixth review session for inference. And yeah, that's all for it. In here, I'm going to walk through normal curve and sampling distributions review for AP Stats. This is our 7th review session for your AP exam in May, which is approaching soon. So let's jump right in. The normal distribution and sampling distributions. And by the way, this mainly covers the contents from Unit 1 and Unit 5, but since this content is just so important that it will show up almost everywhere in different units, so it's just good to know all of the details related to it. So first of all, the normal curve, represented using notations, is like this: a big N with parentheses, mu, and standard deviation inside. So mu in here means mean, and standard deviation just this symbol data. Inflection points, this is where you use x bar plus or minus the standard deviation. And the empirical rule is 68, 95, and 99.7%. So 68 means you are 1 standard deviation away from mean, and 95 means you're 2 standard deviation from mean, and 99.7% is 3 standard deviations from the mean. And this is a visualization of how does it really looks like on a normal curve. A z-score is z equal to x minus mu divided by standard deviation. Also, be able to use z-table and TI-84 calculator to help you draw the normal curve and figure out the standard deviation or the mean, or like the x values labeled on this horizontal line. Check for normality. There are 3 ways. First is using histogram or box plot. So for example, here is, this is not a histogram or box plot, this is a stem plot, but it also can kind of show you is the distribution normal or not. So in here we can say, well, it's approximately normal. And a second way is using empirical rule. So just like I said before, 68, 95, and 99.7% all corresponds with 1 standard deviation, 2 standard deviation, and 3 standard deviation accordingly. And if we just use this data right here for our example, just take a moment, like pause this video and type all of this data into a calculator. Okay, I hope you finished typing. And after you did all of that, please make sure you know how to find, for example, if I ask you to find, well, what is the middle 68% values lie between, you should be able to tell me that it is between 48.6 and 61, which is around 74% of the data. So we expect, our prediction is the middle 1 standard deviation away from the mean. That range should be 68% of the whole data, but in reality for this data set we only got 74%, and same thing as 95% as our expectation, but we only got 93%, and this we got 100%. So we cannot say this is exactly normal, but we can say that it's approximately normal, so normal-ish. And third way is to use normal probability plot to draw a kind of give you a shape of the data. How does it look like to plot it on a normal probability plot? So the more linear it is, the more normal the data set is. And moving on to sampling distributions for means, proportions, and slopes. So for means, this is basically the content from Unit 5, and proportions is mainly from Unit 7, inference, and slopes is Unit 8 stuff. So you can see why I say at the beginning of this video that sampling distribution is extremely important, because it just show up everywhere, and I bet there definitely will be a bunch of multiple choice questions and response questions asking you something related to sampling distributions. And let's go over some key vocabularies first. Sample means subset of the population you're examining. Population means overall group interested in. Statistics. Here are a couple notations for statistics, which basically means the sample. So when you're doing a sampling distribution, the x bar means the mean for sampling distribution, s means the standard deviation for the sampling distribution, and p hat means the proportion for sampling distribution, and beta, it just means, I bet it's slope, right? It's a linear slope. Yeah, it's all Unit 8 stuff. So you can feel free to check my video for that in my playlist. Parameter, those are all the corresponding notations for population. And means, here is a rough drawing for what does a sampling distribution for means looks like. So in the middle, the sampling distribution mean is the same thing as the mean for population, but the difference is this normal curve just made up by a bunch of x bars, so a bunch of sampling means. And the standard deviation means is the standard deviation of the population divided by the sample size, the square root of the sample size. And if n is greater than 30 or the population is normal, then we can say that the sampling distribution is normal. A central limit theorem is larger n means more normal and sampling distribution will be. So basically, the more sample size, the more sampling distributions you get, and you group them together to create this normal curve. The more ends you get, the more normal this curve will be. Proportion, same thing. The mean is the same as the population's, not the proportion. The proportion is the same as the population's proportion, and it's made up by a bunch of p hat. Also, the standard deviation is the square root of pq divided by n. Q is 1 minus p. And you have to make sure that np is greater than 10 and nq is greater than 10. All of those, there are 3 conditions, and the only difference between means and proportions is the third one. So the previous 2s are all the same. So the first one is simple random sample, and the second one is the sample size should be larger than 10% of the population. Also the slopes, and theta is the kind of, you can think of it as the central or the mean proportion, but it's the same thing as the population's beta, and it's made up by a bunch of lowercase b's, and the standard deviation is, make sure you use this notation like sub b right next to this SE to represent the standard deviation for the slopes. And we cannot use any formulas to directly calculate the SE sub b. However, we can use this relationship, which is t equal to b over SE sub b, and arrange this formula a little bit. You can calculate what the standard deviation or the standard error for b it is. Okay, and that's all for this video. And also, this is our last review session for AP Statistics in May for 2026. I hope you enjoy all of those videos and learned something about it. The purpose of those videos is just help you to quickly review all of those vocaps, or just go over them again in your head, and reminds you, well, what should I look at? What should I pay attention to? So anyway, I hope you learned something from it. Thank you so much for watching, and good luck on your AP exam.